So in this video, we're going to look at some basic operations on vectors that are useful for multivariable calculus. Now, I should note some notational things. There's lots of different ways to write vectors, and many calculus books will alternate between these angle bracket notations and the IJK notation. I've opted for the angle bracket notation here mostly because it's easier to type into a Word document than the IJK notation. So that's the only reason that I'm doing that. All of the operations that we're going to talk about are completely equivalent to using that IJK structure. Now, again, we're going to start with some very, very basics, and then we're going to work our way up to some more complex scenarios. So the first thing that we're going to talk about is how to add vectors. And vectors are added together term by term. And so we're just going to add them first term to first term, second term to second term, third term to third term. So 1 plus -5 would give me -4. 3 plus -6 would give me -3. And 5 plus -2 would give me 3. Now, we can also do scalar multiples of vectors in exactly the same way. We would multiply every term by the multiplier out front. And so in this case, -4 times -5 is going to be 20. And then -4 times +1 is -4. And then -4 times -6 is +24. Now, you can also, of course, combine these. So if you had 4 times a vector minus 3 times a vector, then you would just do your scalar multiplications first, and then you would do your adding or subtracting term by term in the same format. The arithmetic basically works exactly like you would think for working with real numbers. Now, the magnitude or the length of a vector is going to be a scalar, and the value is calculated essentially the same way that you calculate the Pythagorean theorem or the distance formula, as if you're calculating the distance from the origin. And so this is going to be, if you've done magnitudes of complex numbers, it works the same way. You just have 3 terms instead of 2. So 4 squared would be 16, and then 9 squared would be 81. And then -5 squared would be 25. You never end up with negative signs under the square root because of all the squaring. And then you just simply add these up. And I end up with 122. And of course, for most vectors, the magnitudes are not going to be perfect squares. If you see perfect squares, that is by design, because if you pick random numbers for your vectors, they're almost never going to come out to be perfect squares. And that's fine. All right, now the dot product for vectors. Now, the important thing to keep in mind about the dot product is this is also going to work term by term. We're going to multiply corresponding terms together, but then we're going to add the results. And so it's very important to remember that for the dot product, you are not going to get a vector out of this. You are going to get a scalar, which is a constant. It is a number. So this is probably the most common mistake that students first learning how to do the dot product will make when doing dot products. The cross product, which we're going to do next, produces a vector. The dot product does not. It's sometimes referred to as the scalar product for particularly that reason, to remind you that it is in fact a scalar that comes out of it. So here, 5 times 8 is going to give me 40. -9 times 4 is going to give me -36. And then 6 times -8 is -48. And then I am going to perform this arithmetic. And I get -44. Again, it is a scalar. It is a number. Now, we're going to see the dot product show up again in some of our more complex formulas, but just as an introduction, this is our basic example. Now, the cross product is a little bit more complicated. To do the cross product, we're typically going to essentially do, if you've done linear algebra, it is essentially a determinant, where we are going to calculate the top row are our component vectors. So they are our I, J, and K components. And then our two vectors go in the rows. 3, -8, and 9. And then as we do these calculations, then we are going to get components of the vectors from these sub cross products. That did not copy the way I wanted it to. There we go. Now, the thing to keep in mind about the cross product is that the J component takes a minus sign, but the I and K components take a plus sign. So this is our basic structure. And then what goes in these parentheses is we're going to multiply diagonally and then multiply on the opposite diagonal and then subtract those two pieces. Now, the pieces that we use, this 4x4 component that we're going to use is going to be not in the column that the component is in. So if we're doing the I component, we're doing the constants in the J and K columns. If we're doing the J component, we do I and K. And if we're doing the K component, we do the I and the J. So let's spell this out. In the I component, this is going to be 2 times 9, which is 18, and then minus whatever we get from this. Now, this is -8 times -3 is 24, right? Positive 24, but we're subtracting it. So we get essentially -6 in the end. In the J component, again, we use the column that we're not, the component is not in. So this is again 2 times 9. And then 3 times -3 is going to be, because it's already negative and we're subtracting it, it becomes +9. And then for the K component, we do these two, the IJ columns. So this is 2 times -8, which is -16. And then -3 times 2, which is 6. And so what we end up with in the end, if we go back to the angle bracket notation, this is going to be -6. And this is going to be -27, and then -22. Now, the triple scalar product is going to work very similarly. Now, the triple scalar product, you can, of course, do this in combination. You can do them in stages. So you can find the cross product, as we did up here, and then do the dot product with the resulting vector. Or you can actually do this process by simply replacing the IJK components with this third vector. And so that's what we're going to do here. I'm going to copy this so I don't have to redo the structure. And the top row is going to become our -8 and our 6 and the -6. And then the second one can go in here and -3 and -7. And then the bottom one goes down here. Now, I will just note that conceivably, if you reorder these vectors, you will get the same answer, but you will get potentially a change in sign. Where we tend to use the triple scalar product is for the volume of a parallelepiped or for a pyramid. Then you want to make the magnitude that you get positive, take the absolute value of it. But that is the most different that it would be by re-scrambling these vectors. Now, again, kind of keep in mind, your cross product is going to produce a vector, but when you dot it, you're going to produce a constant. So in the end, what we're going to end up with here is a constant. And so let's go down to the next line. And again, I'm going to copy the structure to help in typing. But let's think about the contents here. Now, instead of I, J, and K, we have numbers. So I'm going to replace these I, J, K components with the numbers from the top row. 6. And K was -6. So now they're going to multiply. That's why we're not getting a vector. We're getting a number in the end. And then the bodies of these other parentheses, they're going to be calculated exactly the same way as we did before. So I'm calculating the first component from this first column. That means I'm going to multiply these bottom two components from the last two columns. So this is going to be -3 times -1 is 3, and then minus -27, so plus or minus 21. So plus 21, because we're subtracting a negative. And then in this component, because the 6 comes from the second column, we're going to use the first and third columns. So -2 times -1 is +2. And then -2 times -7 is +14. And then we're going to subtract that. And then again, that minus sign out there from the J component, that is still applied here. And then our last parentheses, this is from the third column. So it's these first two that we multiply. -2 times 3 is -6. And then -2 times -3 is +6, but we're subtracting. And so then we just have to do the arithmetic. 3 plus 21 is 24 times -8. And then minus 2 minus 14 is going to be -12 times 6. And then -6 times, and -6 is -12 times -6. 24 times -8. I think I was going to put that in parentheses and I put it the wrong way. Minus -12 times 6 plus -12 times -6. And I end up with -48. Now, again, if you're using the triple scalar product to calculate the volume, you would then make this +48 because volume can't be negative. Now, when we combine some of these together, we have some actual formulas that we can apply. If we want to find the angle between two vectors, we use the dot product and then the magnitude formulas in order to get the cosine of the angle. And then from there, we can find the inverse cosine to find the angle. So let's do this calculation. So we're going to have cosine of theta is going to be, now what is our dot product here? So -4 times 0 is 0. 5 times -4 is -20. And then 5 times 6 is going to be 30. So that's our numerator. And then in the denominator, we're going to have the magnitude. The magnitude of A is going to be 16 plus 25 plus 25, each of the components squared. And then the magnitude of the second vector is going to be 0 plus 16 plus 36. And if we simplify that, we're going to get 10 over the square root of 66 and the square root of 52. Now, to find theta, we would then have to put that into our calculators. Keep in mind that if you put this in radian form, then you will get radians. And if you put this in angle form, then you will get degree form, you will get degrees. So it's a good idea to check your calculator to make sure that you know what answer you're going to get out of it. So I'm putting in 10 divided by, now be careful when you put this in your calculator to make sure that you collect both square roots in the denominator. Otherwise, you're going to potentially get a error, because the number, if you're multiplying by square root of 52, that might make your number bigger than 1. I am getting 1.399 ... for my radian angle. And if I switch that over to degree mode momentarily, that's about 80 degrees. 80.17 degrees. Now, this portion, this denominator portion of this angle between vectors does sometimes cause confusion for the next example we're going to look at, which is the projection, because the projection has 2 copies of the magnitude of A in the denominator, not one of each. And sometimes what messes people up with the projection formula is that the vector you're projecting onto is in the subscript, and that is the one that gets used over and over and over again in the formula. The vector that you're projecting onto that vector, the one that's in the argument of the projection formula, actually only appears once in the formula. And people often interchange these, thinking that it's the B that should be in the formula over and over again, and in fact, it's not. It is, we're projecting onto A, and so A is dictating everything except this one appearance of B. So let's actually do this calculation also. And then I believe this is the last one that we're going to look at. So the dot product. So again, the dot product is, we're going to multiply component by component and then add together. So 9 times 2 is 18. 8 times -3 is -24. And -3 times 7 is -21. And then in the denominator, we're actually going to take the magnitude of A squared, so no square root, but each component gets squared. So this will be 81 plus 64 plus 9. And then this portion is the scalar, and then we're going to have to multiply by the vector. So again, this is another common mistake that sometimes students will make, is that they will just report the scaling factor, but in fact, it is the scaling factor times the vector, because we need to know which direction it is being applied in. And we're essentially projecting it like a shadow onto vector A. All right, so now we need to figure out what the scalar is. So let's simplify our numerator. 18 minus 24 minus 21 is going to give me minus 27. And in the denominator, 81 plus 64 plus 9 is going to give me 154. Which does not simplify. And then multiplied by my vector. And then, of course, you can distribute this through the vector and just write it as a scalar time, as a vector by itself, or you can leave it like this. It is algebraically equivalent.